Let's look at another type of question now. So we want to solve 3 to the 2x minus 5 times 3 to the x plus 6 is 0. And just by glancing at this equation, it may remind you of a quadratic. Obviously it doesn't exactly look like one, but that is the clue here, that we're going to try and convert this into a quadratic to start with. So what we're going to do is we're going to make what we call a substitution, and we're going to say let y equal 3 to the x. So it may not be clear why we're choosing this to start with, but let's just assume this is correct and see what comes out, and then we can discuss how to choose the substitution in a minute. So if we want to then sub y equals 3 to the x into this equation, let's have a think about what 3 to the 2x would be in terms of y. Well, we know that 3 to the 2x, we can rewrite that as 3 to the x squared. Okay, and that's we could use this rule here that x to the ab is equal to x to the a raised to the b. So that's just a rule of indices. And then, well, what is 3 to the x? We said it was y, and so this has to equal y squared. In other words, this first term here is going to be y squared when we sub in y equals 3 to the x. So let's rewrite it here. So 3 to the 2x is y squared, minus 5, and then times 3 to the x, which we said was y, plus 6 is equal to 0. So here's our quadratic now, and then we would like to solve this for y. So let's see if we can factorize that in a double bracket. So y minus 2, y minus 3, and then we know therefore that y is equal to 2 and y is equal to 3. So it may be tempting to say this is the answer. However, when it says solve in the question and the initial equation was in terms of x, really what they're asking for is solve for x, not solve for y. So this is not the final answer. Y is equal to 2 and y equal to 3. So then what we have to do is remember that, well, we said y was equal to 3 to the x. So therefore we know that 2 is equal to 3 to the x. And 3 is equal to 3 to the x. And now we've got these two equations and we need to solve them. And this is where potentially logarithms will come in. Remember that whenever we're trying to solve an unknown, and the unknown is to a power, then we use logarithms to do that. However, this bottom one here, 3 is equal to 3 to the x, we actually don't need logarithms for this. Sometimes you could just work out the answer just almost in your head. So in this case, the bottom one, x has to equal 1, because 3 to the power of something gives 3. Well, remember that 3 is the same as 3 to the 1, and so x has to equal 1 in this case. But certainly for this one up here, 2 is equal to 3 to the x, we definitely need to use logarithms for that one. So we can take logs on both sides to base 3. So that would be log of 2 to base 3 is equal to log of 3x to base 3. And then remember that we can take the x down the front using one of the log rules there. So that will become x log 3, and then log of 3 to base 3 is just 1, so basically we can get rid of this completely, and then we know that x has to equal log of 2 to base 3. You can leave it like that, or if they ask you to say 2 or 3 decimal places in the question, you could just put that into a calculator and evaluate that. So that is how we would solve this kind of a question. Once you've seen it once or twice, you should be able to easily spot it. So the key is to make a relevant substitution. Now, how do we choose the right substitution? Here we said let y equal 3 to the x. The best way to do it is really whatever this term is here is going to be your y value. Okay, so have a look at whatever that is, and that will be your substitution. There is one slight variation which I should mention. I have seen the odd question on occasion maybe rewriting this middle term instead of 5 to the times 3 to the x as 5 times 3 to the x plus 1 or something like that as your second term. Now this doesn't come up very often, but if it does, even here I would use y is equal to 3 to the x. So ignore the plus 1 and just take this as, again, your substitution. But as I mentioned, that's a very rare case. Most of the time the second term would be very nicely written, like 5 times 5 to the x or 2 to the x or something like that. And so whatever this term is here in your bracket will be your substitution. I just want to go through one modification of the previous question. I have seen this come up on occasion as well. So imagine we had this equation, we want to solve it again, and again it looks roughly like a quadratic, and we want to choose the relevant substitution to create a quadratic here. So again, looking at this second term, 3 to the x, so that means that our substitution is 3 to the x. But the thing that I really want to focus on here is this term here, and specifically how can we rewrite 3 to the 2x plus 1 in terms of y when y is equal to 3 to the x. So this again comes down to understanding indices, and please refer to my video on indices again if you're not clear, but we'll go through this process. So 3 to the 2x plus 1, that is actually going to be 3 to the 2x times 3 to the 1. Okay, now where does that come from? Well, that comes from this rule, x to the a times x to the b, and that is equal to x to the a plus b. Okay, now, so in this case, in our question, x is going to be 3, and we could say a is 2x and b is 1. And so what this rule here is saying is that we can actually add those powers. So a is 2x, b is 1. So when we add those two powers, we get 3 to the 2x plus 1. So I see that this is a very common mistake with a lot of students. So then what we can do is we can say that, well, we know that 3 to the 2x, remember that we had that in the previous question, that was our y squared. And so actually this is going to be 3y squared. So 3 to the 2x plus 1 is actually 3y squared when y is equal to 3 to the x. So if we were to continue this question, I don't really want to go through the method because we already understand it, but our first step then would be 3 to the y squared minus 5y plus 6, and then you would proceed to solve this, and then solve for y, and then work out what x is after that, as we did in the previous question. But the thing I really wanted to home in on specifically is the fact that 3 to the 2x plus 1 is actually 3y squared when we choose that y is equal to 3 to the x. Let's now look at the concept of natural logarithms. So what is a natural logarithm? Well, a natural logarithm is a logarithm to base e specifically. Now what is e? E is actually a special number in maths. It's approximately 2.718, and it's a number that naturally occurs in nature. So a parallel would be the concept of pi, 3.14, etc. And just like pi e actually goes on forever in terms of the digits after the decimal point. So any log that has a base e, that's what we call a natural logarithm. And a little bit of notation, if we wanted to take, for example, log of x to base e, we don't write log to base e, we actually write ln x or ln x. So this ln x means the same as log to base e, and from now on in the calculations we will assume that ln x is log to base e. This would be a good time to have a look at graphs of y equals e to the x and y is equal to ln x. So I've drawn them here. So let's have a look at a few properties. So y is equal to e to the x, it looks like this. And an important thing to note is it cuts through the y-axis at 1, and there's an asymptote over here. So remember, an asymptote is a section of the curve where the curve approaches an axis or a certain line, but never actually touches it. Okay, and if we look at y is equal to ln x, it looks something like this, and there is again an asymptote over here, so ln x doesn't actually touch the y-axis over here, it just approaches it, and this value here is 1. Okay, and you may notice that they look very similar, they're almost reflected, and that's an important thing to note, that actually e to the x is the inverse function of ln x. So they're both opposite operations, so they cancel each other out. And we spoke about this in another video, that if you've got an original function and an inverse function that does the opposite, one of the curves will be reflected in the line y equals x to get the other curve, and that's what we can see here, that if we were to draw e to the x and then reflect it in the line y equals x, then that would produce y is equal to ln x. So I would definitely be aware of what these graphs look like to memorize them, and then sometimes in the exam they may ask you to draw a transformation of one of these graphs, but please refer to previous videos on graph sketching for the transformations. But as long as you understand what e to the x and ln x look like, and you understand the process of transformations, then you can really draw any graph that they could ask you related to e to the x or ln x. One other thing to mention is I have seen questions where they don't want you to sketch something to do with ln x, but they want you to sketch some the graph of log of, say, base a x. Okay, so remember that y equals ln x is log to base e, and if we say a is any number, well, this graph essentially looks the same as ln x. It still cuts through the x-axis at 1, and there's an asymptote over here on the y-axis. Let's have a look at a question. So solve ln of 3x plus 2 is equal to 2. Give the answer in exact form. So I just want to emphasize that all the methods that we've looked at involving logs, how to solve log equations, all that is exactly the same whether we've got log or ln. But you just have to remember that ln means log to base e. That's really the key to doing any of these kind of ln questions. Okay, so how can we apply that here? So, well, we can remember that ln, remember, is log to base e, so we could maybe rewrite the question like that. You don't have to rewrite it as log to base e. You could just keep it as ln, but it might help you sometimes to remember what's really going on. And then we want to solve this, so remember that means we want to get x equals, so that means we want to remove the log. So we're going to use that rule that says that log of b to base a is y. If that is true, then a to the y is equal to b. And so in this case then it's going to be e squared, so e to the power of 2 is 3x plus 2. Now what do we do here with this e squared? Well, remember e is approximately 2.718, so you could just replace e with 2.718 and square it, but remember it says give the answer in exact form. We spoke about this before. Essentially exact form means the opposite of giving a decimal answer, so you can keep e in the answer. If they say give it the answer in exact form and you've got e in the question, then you want e in the answer. You don't want to evaluate e with a calculator. So that's what we're going to do here. So we want to make x the subject, so we can take 2 away from both sides and then simply divide by 3 to get x on its own. So that would give us the answer. So x is equal to e squared minus 2 over 3. So that would be exact form. Let's look at another question now. So we want to solve ln of x squared minus 3 ln x plus 2 is 0. And again, this should remind us of a quadratic. And we're going to use a similar method to the previous question where we just take a relevant substitution. So we're going to look at the second term again, and that will help us in determining the substitution. So we're going to say let y equal ln x, And then when we sub it in, we should get y squared minus 3y plus 2 is 0. And then let's see if we can factorize that. Hopefully it will. So y minus 1, y minus 2. And when we then proceed to solve that, we have y is equal to 1 and y is equal to 2. But remember that y was equal to ln x, so y is equal to ln x, 1 is equal to ln x, and 2 is equal to ln x. And how do we proceed to solve that? Well, remember that ln is the same as log to base e, so we can say that e to the power of 1 is x, or x is e, and also x will be e squared. Let's look at another question. So solve e to the x minus 3 plus 3e to the minus x is equal to 1. So this is a very unique looking question. We haven't seen anything like this before. So the way we can do this is the first step with these, it's always going to be the same first step, is to rewrite e to the minus x as 1 over e to the x. So that would always be your first step with these kind of questions. So let's do that then. So that will be e to the x minus 3 plus 3 over e to the x is equal to 1, because we're timesing 3 by 1 over e to the x. Then we're going to clear the denominators. We want to remove the denominator. So the way we do that is we times both sides of this by e to the x, because that's the denominator. So e to the x times all of this. And then when we do that, it's going to be e to the x times e to the x, which is actually e to the 2x for the first term. Now let's just make sure that that's clear why that's the case. So e to the x times e to the x, we're going to use x to the a times x to the b, that rule of indices, which we're told is x to the a plus b. And so what that's saying is we can add the powers, so that will be e to the 2x. So that's the first term. Then the next term will be minus 3 times e to the x plus 3, because we're doing e to the x times this, and the denominator will cancel with e to the x, so that will be plus 3 is equal to e to the x. Then we want a 0 on one side and everything else on the other. So I'm going to take the e to the x to the other side, so that would be minus 4e to the x plus 3 is 0. And the reason why I wanted to get a 0 on one side is because, again, this looks like a quadratic, so we can then say let y equal e to the x. So remember, we always tend to look at that second term to get a clue to the substitution. Then this will become y squared minus 4y plus 3 is 0. Y is equal to e to the x, so e to the 2x will be y squared. And then let's check if we can factorize this as usual and solve. So that should be y minus 1, y minus 3, and then that means y is equal to 1, and remember y is also e to the x, and then y is equal to 3. Again, that's e to the x. And then how can we solve these? Well, if 1 is e to the x, so e to the power of 0 will give us 1. So x is 0 for the first solution. And then the other solution, how can we solve this one? Well, again, remember, whenever we're trying to get solve an unknown power, then we take logs. And in this case, because it's actually e to the power of something, let's take log to base e, or ln of both sides. So it will be ln 3 is equal to ln of e to the x. You could then take the x down the front, x ln e, and ln e is actually 1. Okay, because remember, ln is log of to base e, and therefore log of e to base e. How do I get from e to e using powers only? That has to be 1. So ln of e is 1. That's an important thing to be aware of. And so therefore the other solution will just be x is equal to ln 3. So here are our solutions. X is equal to 0 and x is equal to ln 3. So just to recap then, whenever you see this kind of equation with e in it, and specifically e to the negative x, then it's always this method. First step would be to rewrite e to the minus x as 1 over e to the x, sub it in, and then the next step would be to clear the denominators and then form a quadratic after that. Let's now look at the concept of logarithms and nonlinear data. So on the left I've drawn this graph y is equal to ax to the n. So a and n are numbers or constants, and if we have a look at the graph, it's curved, it's what we call nonlinear, and on the axes we've got y and x. However, if we look at this graph on the right, we notice that it's a straight line, it's linear, and the axes are now not y and x, but they're actually log of y and log of x. So what we can do is, if we have some data and we know the original data is given by a certain equation and the data is what we call nonlinear, if we now plot the data on a new set of axes with log of y and log of x, this data now becomes linear. The data now can be represented by a straight line. So how can we show this? Where do we get this straight line from? What we can do is we can go to this original equation and we can take logs of both sides. So let's just say we're going to take logs of both sides. So log of y is equal to log of ax to the n, and as long as the base is the same, we can take logs to any base we want. So let's have a look at how we can pull apart the right hand side. So we can use rules of logs here and say that's the same as log of a plus log of x to the n, and then we can take the n down the front. So we have n log x. So here's our equation now. We have log of y is equal to log of a plus n log of x. Okay. Now we said earlier that a and n are constants. So therefore, if a is a constant, then log of a is also a constant. But x is still a variable and n is a constant. And so what we could do with this equation is we can draw a parallel between this and the general equation of a straight line y is equal to mx plus c. Okay, so in other words, this value, this constant, is now going to be our c value, and then n is going to be our gradient, and then log of x is kind of equivalent to our x value for y equals mx plus c. So if you were to now change x and y on this axis to log of x and log of y, then what we can say is, we could say that this graph must cut the y-axis at the c value being the log of a, and then its gradient must be n. Okay, so if you have some kind of general equation describing some data, maybe in a scientific experiment, and that equation is given by y is equal to ax to the n, you could then create a linear situation for the data, changing the x and the y-axes to log of y and log of x, where this straight line will cut the y-axis at log of a, and the gradient of the line will be n. Let's have a look at another type of equation. So in this case, we're going to look at y is equal to a times b to the x, and in this case again, a and b are constants, and we would like to understand how we could draw another linear graph, maybe containing logs again, similar to the previous question. So I've plotted y is equal to a times b to the x approximately here, depending obviously on what a and b are. It would look something like this. And now let's try and form some kind of linear equation from this situation. So let's take logs again on both sides. So we're going to have log of y is equal to log of a b x, and then we would like to pull the right hand side apart, so we're going to have log of a plus log of bx, and then that will be log of a, and we're going to take the x down the front, x log b, so log y is equal to that. So we would like again to compare this to the straight line equation y is equal to mx plus c. I'm actually going to just swap the order c plus mx because it's easier to compare it like that. Now we can see that log of a is going to be our c value. That was similar to the previous example. But now this is slightly different. We've got an x in both of these, and so now m must be log of b. So in other words, the gradient is going to be log of b. But in this case, we're going to draw our new equation, and the axes are now, instead of y, we're going to have log of y again. That's fine. It's the same as the previous question. But here, in this case, we're still going to have x on this axis because x remains in this equation here. So if we were to draw this out roughly, again it'd be a straight line, and again it would cut over here at log of a, and now the gradient is going to be log of b. So that would be how we would convert y is equal to abx into a linear form. So again, it cuts at log of a on the y-axis, but now the gradient is going to be log of b. Let's have a look at this question. So we've got figure 8 shows the graph of log of y to base 10 against log of x to base 10. It is a straight line passing through the points 2, 8 and 0, 2. Find the equation relating log of y to log of x, and hence find the equation relating y and x. Okay, so let's have a think about how we can do this. So the first thing we can do here is we can actually work out the equation of this straight line using just familiar y equals mx plus c theory. So first of all, we know that the c value of this equation has to be 2 because it cuts through the y-axis at 2. And now we need to work out the gradient of this line. So that would simply be change in y over change in x. So we can construct some kind of right angle triangle underneath and just do the change in y over change in x. So this height here will be 6 and this width here will be 2. So 6 over 2 is 3. Okay, so the equation of this line has a gradient of 3 and a c value of 2. Okay, but we have to also be conscious of the fact that on this axis it's not y but it's log of y, and on this axis it's not x but log of x. So what we could do is we could write the equation as log of y to base 10 is equal to mx plus c, but m in this case is 3, x in this case is actually log of x to base 10, and then the c value is 2, that's fine. So what we can then do is we can take the 3 to the top using a relevant rule of powers of logs. So then we can say that's going to be log of x cubed to base 10. And now this bit's a little bit hard to spot, but we would like to rewrite 2 in terms of logs, and specifically logs to base 10. So we can actually write 2 as log of 100 to base 10. So that might be a little bit hard to spot. Typically at this point we've typically gone from, say, log of 100 to base 10 back in this direction, but we haven't at this point gone from 2 back in this direction. But it should be clear that log of 100 to base 10 is going to be 2. And then what we can do is we can combine these two logs as one using the relevant log rule. So that will be log of 100 x cubed, again to base 10, and that's going to be log of y to base 10. And then what we can then do is just cross these logs out, and that will give us y is equal to 100 x cubed. So this will be our equation relating y and x in this case.